much. Thanks to the organizers for inviting me. It's my first time here. It's awesome surrounding. I hope to enjoy the plenty of hikes that are going to come up. Also, I have to apologize because I put it in parentheses already at this stage because I fear that I'm not going to get to the graph part, which is maybe not that bad given that I think the audience is more interested in the group part. But feel free to ask me questions about the graph part. He knows this already. The talk is not for him. So indeed, the point of this talk is just to do cohomology with differential forms. Now, this may sound crazy to some of you, but depending on where you grew up, this is the most natural thing to do. So let me just remind you how this goes in this particular case of GLN that I'll be looking at. So I'm looking at the space of positive definite symmetric matrices. I'll denote this Pn, and this is just matrices of an X, so they have to be symmetric, and they're supposed to be positive definite. So what I mean here, so think of them as n by n matrices, and positive definite means that for every vector that's not 0, this product here is positive. It's a very classic thing, just positive definite real symmetric matrices. And somehow the idea is that by looking at differential forms on the space, we can compute group cohomology. So maybe I should tell you how this is space related to group. So the first little exercise you can do is that there is an isomorphism. So if you take GLN, and you take the right cosets with respect to the orthogonal group, so the maximum compact subgroup, you can think of these cosets just as one way of parameterizing Pn. What you do is you take an element here, a little invertible matrix G, and you send it to GG transpose. That's clearly a symmetric matrix, and then you take a vector. So what is V transpose, GG transpose, V? It's just the norm of G transpose V squared. So indeed this is positive definite. You can check that this is surjective. So this is the exercise. In particular, every positive symmetric matrix has a unique square root. So if you have a matrix in Pn, there is something you can call x to a half, which is uniquely defined by the properties that this is also supposed to be positive definite symmetric, and that it's a square root. Right, it's symmetric, so the eigenspaces are orthogonal, so you can go to an orthogonal basis and it becomes diagonal, and then you take the square root of the eigenvalues. So this shows you that this map is surjective. And if you just look at what the kernel is, well, you can convince yourself that this is also effective. Model out exactly. So, for example, how do you get 1? Well, 1 is exactly orthogonal, and the whole thing acts transitively. So this is the exercise. And so we have one way to think about Pn from this group. And now, of course, on the set of right cosets, you can still act with the group from the left. So you get the left action from the group on Pn. I draw it here, though. And how does it act on a matrix by Gx, G transpose? And some of this is what we want to exploit. One other thing to note, which is important, is that this space Pn is contractible. Actually, it's convex. So you can actually contract everything to the identity matrix and stays positive definite. So there's no interesting cohomology on this space, but now we still have a group acting on it, so you can go to the quotient and compute the cohomology of the group. by the cohomology of the quotient space. So one thing I should say for this is also a statement about the stabilizers. So a further remark. So the stabilizer, let's say, of the identity under this group action, right? That's what I told you. This is On. And the stabilizer of any other element is just a conjugate. But in particular, it's this compact group. So if you intersect it with a lattice, it will be a finite thing. So this thing has finite stabilizers if you think now of the subgroup of GL and Z acting. Okay? So if you have Pn, and now you think of the action by GL and Z, and this has finite stabilizers. And the conclusion of all of this is that you can take this space, you can look at the quotient by GL and Z, and if you look at this topological space and you compute its cohomology over Q, let me just put R here because I'm going to integrate later anyway, that the cohomology of this space is isomorphic to the cohomology of the group. I mean, at least the way I learned it, that's where group cohomology originally comes from. Oh, I have to erase this later. Okay. So I want to study the group cohomology by the cohomology of this quotient space, and I want to use differential forms. So you know, if this would be a smooth manifold, you know the Ram theorem that you compute cohomology by. One way to compute cohomology is by computing the cohomology of the complex of smooth differential forms. Now here you have a quotient, so you can do two things. Either you can literally try to think of smooth forms on the quotient. It's a little bit tricky because it's an orbifold, so it's not really smooth, so there's a little... but equivalently, when you have a quotient, you can look at the equivariant forms on the total space, so that's what we're going to do. So I just look at differential forms on Pn, and if they happen to be invariant under GL and Z, you put them in the machinery and you can integrate cycles on the group over these forms, so you get a cocycle, and therefore the cohomology class. So all we need is some differential forms on this space. That's all I say here. So what we want is a GLNZ invariant differential forms, smooth differential forms, say, on Pm. So here I mean smooth differential forms. And this would be great, you can do a lot with that, but this is also quite a tricky problem to compute GL and Z invariants, and somehow we're doing the simplest possible baby case of this. We're looking at GL and R invariants. So what we do is GL and R invariant. And then to these, you can associate a form in the cohomology. So on one hand, you might think this is harder because you have more constraints, well, in a way that also makes it easier. But in particular, this is in the end, this boils down to algebra because the group GL and R acts transitively. So actually a form is uniquely determined by what it does at a particular point, so it's all just some version of relative Lie algebra cohomology. So if you know this kind of stuff, you can compute these invariant forms with the known results from the literature. So just a remark.
So you want to make it to be close to you, right? You want a GL and Z invariant closed form.
Yes, I want it closed, yeah. So there's another little extra miracle that those ones turn automatically out to be closed. But yeah, you're right. If I do this, I have to be more careful. I'll check that. So the remark is such an omega here, such omega is determined by its value at the identity matrix. Right, so what is this? This is just some element of the exterior algebra of the cotangent space at the identity of Pn. And if you think about what is this, this is somehow the Lie algebra GLN mod SON. It's all the matrices modulo the antisymmetric matrices. So within that tensor algebra of this quotient of Lie algebras, you're looking at the invariance with respect to the adjoint action, and there is a whole formalism for this that I don't want to talk about. I just wanted to tell you that this is something that there are tools for to compute. So you can actually compute what are all the GL and R invariant forms on the space. But if you don't want to do that, I can just give you an example, and we just work with that. Perhaps I should make one more comment. I'm happy to say more about that if you want to know more about it. There's, of course, a general way how to cook up differential forms associated with some topological space with some nice action and a bundle on it. This is the whole Chern-Weil theory. So if you have a bundle and some curvature, the connection, there's a curvature, and you can do the Chern forms and so on. And actually, all of this can be put in this context. So if you want to know how that works, I'm happy to explain it. But for the purpose of this talk, I will just march on. So what we do is we just define something. I'll call it beta k. So x is, capital X is my matrix, it's just my canonical coordinate on Pn. And I look at this thing, takes x inverse dx. So this is a matrix whose entries are bond forms. Okay, that exists. We take the kth power, still a matrix, but now the entries are k forms, and I take the trace. Okay. Now that's a k form. So this is a k form on Pn. And here's an important comment that actually you can take a fixed k and think of this form on different spaces of matrices. Yeah? You can take the x inverse dx to the 27th power and think of that as a form on the space of 3 by 3 matrices, 4 by 4 matrices, 5 by 5 matrices. I'm stressing this because there's some confusion that comes from that one can get into if one forgets the fact that one has to actually, if I only give you this, I haven't told you that yet what space I'm actually thinking about this as a form on. So
should I think of this as a function in x? Or like, I mean, you have x in like 3 parts there, and you don't plug in a specific x for dx.
Previously, personally, I don't like to put it there.
Yeah.
So this is really a differential form on this space. Yeah. X is the coordinate on that space.
Yeah.
So I'm using x inverse dx to just write down in coordinates what that form is. So if I write beta subscript, it would normally be the restriction of that form to a particular point at that. But somehow we stuck with this notation because it's convenient to write down, to pull back on this form when you do something to x or so. But maybe you would be happy if I don't put it there. I mean, I would be happy if I don't put it there.
We're very happy to make you be happy, so you could take the x away.
Okay, these are forms. Now, why are these good forms? Or maybe I do this here. So we want them to be invariant and closed. And I just touched the screen. That's not so properties or exercises. Maybe I do the first one. Yeah, so now I do this horrible notation. Dx G transpose, yeah? So what do I mean here? Take the group action for a fixed G, so the thing that takes X, and maybe I should write this. So we have this group action psi G of X is G X G transpose. And what I mean by this really is the pullback under psi G of this form, beta k without a subscript, but I write it like that. Well, we just put it in there, so we have the trace. So what's the inverse? So minus t, I mean the transpose and inverse, x inverse, g inverse. Then the differential only acts on x because we have fixed g. With a fixed g, we're looking at what does this do to the forms. Dx g transpose to the k. Now all of these cancel. Then of course if you raise it to k, also these things cancel. So in the end, You got G inverse transpose, and then all this stuff in the middle cancel. And then because the trace is cyclic, you can also move this around, and this also cycles and you're done. Okay, so they are invariant. Good start. And so there are some extra things to say. So many of them are actually 0. So the even ones are 0. That's just some. All of these properties are rather straightforward to prove. So we only look at the odd ones, and the odd ones also half of them are 0. So all of those that are congruent with 3 or 4, they are also 0. So we're left with only a fourth of all of those forms being non-zero. But those that are left over are indeed closed. The 4k plus 1s, they're closed. And invariant. And I should say one more thing. That there's also some vanishing that depends on the size of the matrix. Somehow if your matrix is too small, obviously you're on a small dimensional space and you can't have a very high degree form, but there's actually a stronger vanishing result. That if you're on, so this form beta 4k plus 1, viewed as a form on Pn is 0 for n less than 2k plus 1. Yeah, so if your matrix is too small, these higher beta forms will vanish. That's, all of these things are pretty straightforward to prove. I'm not going to compute one explicitly because these things turn out to be quite big expressions. And actually computing them in practice is not at all easy. So we have situations where we could compute the integrals if we could compute the form. It's quite embarrassing, but let me give you one example. Beta 1, that's a 1 form. It's a trace of x inverse dx. It's a trace of d log of x. And there's some little algebra. It's the same as d log of the determinant. So this form plays kind of a special role. In particular, I've already announced for you primitives. It does not contribute to cohomology. Yeah, it's only measuring this kind of cone direction of the space, which is just the overall scaling. So we will not use that as a differential form. It doesn't give you a cohomology class because it's exact. But so we have this, okay, and now we can already, from this principle, conclude that there are lots of forms. So indeed we have some classes. So for example, we have the form, well, there's of course a constant function 1. I mean, that's an invariant closed form. And that corresponds under all of these identifications, of course, to H0 of any GLNZ. Of course, we have this. But then already with the next one gets interesting. So what about this beta 5? So this is the first one. This is the 5 form. And I just explained to you it vanishes on 1 by 1 matrices. It vanishes on 2 by 2 matrices. The first time you have it is for 3 by 3 matrices. And so the first time you could possibly try to think about this form would be in H5 of GL3. But as I told you, right, you could also think of this. There's a different class, which I unfortunately denote by the same symbol. There's also, it can also be interpreted as a class in H5 of GL4. Or as a class in H5 of GL5. There's actually, in principle, you could try to interpret this form in infinitely many cohomology groups. And then there's also products. I mean, this whole thing is an algebra, right? If the forms are closed and invariant, then all of the products are closed and invariant. So you can also look at things, for example, beta 5, wedge beta 9, the class of this, which is of course the product of the classes. So this will be a 14 form. And for beta 9 to exist, to be non-zero, you need at least 5 by 5 matrices. So this starts at GL5. But you can also view it in GL6 and so on. Yeah.
Quick question, and tell me if it's not easy to say why, but you have in cohomology, of course, you have restriction maps to the subgroups. Is it immediately clear from the formula that the beta k restricts to beta k?
Yeah, so I mean, you can, it's not obvious, you need to know the direct something, right? So, but if you think of the morphism from GL3 to GL4, is that the question?
Yeah.
Yeah. So if you think of the stability story that was mentioned already today, that there's an obvious map from GL3 to GL4, so there's a pullback map from the forms from GL4 to GL3. What does it do on matrices? It's the block diagonal decomposition. So you need to know what do these beta forms do on blocks. So let me tell you. So if you have beta k of a block matrix, x, y, it's beta k of x plus beta k of y. So if one of your blocks is a 1 by 1 block, that beta will always be 0, and you just indeed get the beta on the smaller. So if you just do the 1 by 1, indeed. So these different maps, I can map, so the maps here, it's commuting.
Yeah, the other way around.
Oh, sorry, the other way, yeah.
No, you're good. So that's a good reason why they have the same name.
Indeed. So they do give you the stable cohomology classes because they extend to all. But some of the point is that, as I said earlier, sometimes it's important to distinguish where you're actually viewing that form, because sometimes it's 0, sometimes it's not 0. So now we come to the red herring in the room, right? I've written down lots of classes for you, and are they actually all 0 or not, right? So the question is, how can we answer that problem? Can we figure out if any of these forms are actually non-trivial? So there's one theorem. I'll attribute it here to Bismuth and Bloch, but I think in a weaker form it's been known longer, but Bismuth will not give an explicit primitive of the form. So if you think of this beta 4k plus 1, as I said, the first time you see it is in GL 2k plus 1. That's the first time where the form is not 0. The form is a non-trivial form. So this is 0. And so the first time it appears, for example, for a 3 by 3 matrix, the beta 5 is 0. Yeah, so this class here is 0. But you can ask, okay, it's 0 here. If you know about the stability results, you know that eventually it's going to be non-zero. But the question is, where does it start to become non-zero? What happens with all the others? So you already know that if you want to think of these as classes, you have to get rid of the last one that's even possible. And then the result is that all the others are good. Yeah, so the theorem, so this is Francis drawn in a paper from a few years ago, is that if you take this algebra of all of these betas, and now I'm getting into trouble, 4k minus 3. So here I mean the alternating free algebra. So this is a finite dimensional space, and it's also because all the betas are odd, right? You can't take any of them twice, so either in or out. So the dimension of this thing on the left, that is 2 to the however many letters I've written. So this injects. And of course then, by these inclusion maps also, it continues for the future. But actually, part of my talk is to talk about what happens at the next step in the even case. So I told you this beta 5 is 0. I'll skip over this one for a second. But over here, if you think of the beta 5 class H5 GL5, that's definitely non-zero. That's part of that theorem. Yeah? So this class here, this is not 0. Yeah, so we've constructed the class in H5 GL5. Of course, by this vanishing and the cup product, you know that also all the polynomials of this one and the other ones are all 0. So if you go to GL3, GL5, this is all you get from this whole process, right? You only get this beta 5, and you have the triple class, and that's it. Yeah, but if you go to higher ranks, you get polynomials of these things. You get exponentially many different products of these betas that you can get there.
Was the statement of the Brown theorem about like the vector space generated by them, or a ring generated by them under Brown?
This is the ring generated.
Okay.
This is the alternating ring, pre-alternating ring.
Yeah. So in here you have the beta 5, beta 9. All in there.
Okay, great.
Alternating algebra.
So does the beta 5 what beta 9 represent? I remember a non-trivial class for GL5 in page 14.
Yeah, so let's think about this one. So if you think about this one here, so the beta 9 shows up for the first time in GL5. But that means this class here, viewed as a class on GL5, this is 0.
Oh, so you don't get it.
Sorry, what did I say?
That's busy.
Yes. This is 0.
Yes. And so the cut product is
So
0.
therefore, this is also 0. But if you go to GL7, you have it. Yeah? So if you're in GL7, there beta 9 is non-zero, and also the product of beta 5 and beta 9.
Ah,
So here you have a non-zero beta 5 wedge beta 9. This is not 0. Yeah, so 5 by 5 matrix is the first time you have a non-zero form, but it happens to be exact, so you don't get a cohomology class. Starting at 7, actually the form is not exact, and you get the non-zero cohomology class. Does that make sense? It's actually very, very important because a lot of confusion comes from these viewing the same form at different degrees, kind of. And you know by stability, if you know the stability result tells you that if you fix the degree and you go to big enough matrices, you know what these cohomology groups are, right? So for a fixed degree, I mean, you know, in small degrees, there's only a finite set of monomials I can write here because the degrees grow with these things, right? So if you fix the degree, there's only a finite product number of monomials and betas you can ever write down. And the statement is by stability that for large enough matrices, they will all inject. But of course, for very small matrices, those classes will not yet be there. So the question is, when do they switch on? And some of this theorem tells you exactly where they switch on.
so that's the class that we found with Bertrand and Soulé. Was that?
Sorry?
So there was one in GL7, if I recall correctly, around this.
This is there. This is a non-zero class.
Exactly the one?
Yes.
Okay.
So this is optimal given Bismuth law.
Yes.
There's one class. I mean, there's one. The even is missing now, but he's going to tell you about that later.
I'll talk about the even later. Yes.
So we don't know optimal yet, but
We'll talk about graph and then talk about that one. Okay. So my plan was to tell you a little bit about how the proof of this works, and then tell you something about what happens in the even case, and then say something about the Hopf algebra. So I have to hurry up. So let me just give you the basic ideas. Sketch. So how do you prove that any of these, so we have defined these classes, how do you prove that they are non-zero? You pair it with something else and show that the pairing is non-zero. So what do we pair it with? So we better have some duality. And shall I write this here? So we just heard about the Borel-Style duality using the Steinberg module. That's the algebraic way to compute the dual of this. I want to use the geometric way to compute the dual of this, which is Poincare duality. So I want to use Poincare duality. So what does Poincare duality give me? It gives me a map, so I have, let me write it here. It gives me a pairing between this cohomology group of this space that I have identified with the group that I want. And now I go to the complementary degree. So it's something like n plus 1 over 2. The complementary degree of the same space. And now I have to say some things. First of all, I have to take compact support because this space is not compact. And then furthermore, you have to ask whether or not the space is orientable. Now in the odd case, for n equal odd, this is orientable. And I'll just put R here. For the even case later, I'll have to swap this with the orientation bound. Yeah. For the moment, it's just this. Fine. Now how do I write down a form with compact support? Well, I don't know how to do that, right? Because I can write down these traces of x's and inverses, whatever, but if you work these out, these are algebraic forms. So in terms of the coordinates, you know, there's some inverse, there's a determinant in the denominator. How do I write an explicit company supported form to choose some bump function? No, that's not what I want to do. So I'm going to replace this by using a compactification. Yeah, so if you have, so I want to view this space here. Ideally, first of all, I can't write all of this here. Let me continue over there. So the first thing we're going to do is already hinted at that the fact that there's this scaling degree here that's picked up by beta 1, that's just scaling the matrices, the diagonal action, the action by the center of the general linear group, doesn't contribute to the cohomology. So we can just get rid of that and work projectively. That has the advantage that we start already with a projective space. So instead of viewing of all the matrices, we model out by scaling all the entries by the same scalar. Then we can start with a projective space. But then the problem is that these forms will have singularities on the boundary, because if you set enough of these entries 0, the determinant, the x inverse will not exist, and you get poles. So there's several problems you have to fix. So let me do them one by one. So what we first do is we replace this quotient by what we call the link, where this link is essentially the quotient just by, now there's two different ways to write this. So what I really want to, I want to take the quotient by the center of the action of the of GL and R, but of course that's just the scalar matrices, scalar times the identity matrix, but it acts G transpose, so it acts by a square. So I'm only modeling actually out by positive scalings of the matrix. If you could also think of this as kind of the projective version. Now we have to compactify, because I want to use a representation of this completely supported cohomology by viewing this as an open in the compactification. So I have no time to explain what that is, but what we're going to do is we're going to take this and then we're going to blow up certain loci that correspond to matrices developing a kernel in a systematic way. And I stick to the notation in the group, so we construct a variety L, A, G, drop, fortified. Yeah, so you take this thing, you're adding the matrices which have rational kernel, but then you have to do blow up certain subspaces, exactly those subspaces where these forms develop poles. So you get a variety here. It comes with a divisor that we call the boundary, which is a closed, such that the complement is what we want, such that this quotient is literally the open. And whenever you have this situation, when you have an open written as a complement of a compact and a compact, then the compactly supported cohomology is the same as the relative cohomology. So you just take the two sequences, and you see that on the compact pieces, they have isomorphisms. And
in what sense is this a variety?
In a simple sense. So the framework that Panzer has developed for this is that you really work with this. So you work with an ambient variety, like the projective space of a certain. You have a vector space, a projective space around it, and in that you have.
Maybe it's helpful to say it's a Satake compactification.
If that's helpful to you, then I can say that. So it's constructed by algebraic blowups, and in that you're looking at this real locus that's maybe cut out in a different way. But there's a complex variety ambient that's there. I don't know if that satisfies you. I suggest we discuss this.
Isn't it all-dimensional sometimes?
I mean, it's not a. You talk about a real half-dimensional cycle in the complex dimensional. It's the usual story. You take a look at the real set, the real simplex in projective space. Projective space has complex dimension, the same as the real dimension of the set that you're looking at. I think it's really. I'm not going to be able to satisfy you in the remaining 2 minutes that I have or whatever for this, but I'm very happy to discuss this with you.
An easier question is, what is small g?
Yeah, G's in. Good question. So it's not really a variety in that sense, but what we do is we cook up a formalism where this thing is realized as a. So you take lots of little cones, you glue them together. It's a kind of complex like that, where each piece has an algebraic structure, and you show that the whole thing fits together, and then you can use the Poincare lemmas and everything from the piece to show that you still have the comparisons that reflect exactly that with this background. Sorry, I can't say more than that.
It's a diagram of varieties, right?
It's a diagram of varieties, maybe that's good. So the upshot is that this compactly supported homology group is isomorphic to the relative cohomology group of this modified topical moduli space relative to its boundary. Now, why did we have to do this nonsense and just not work instead with a simpler compactification, right? I mean, the point is we want to make sense of these differential forms on the space. So we have to find a compactification such that our differential forms actually extend to that compactification so that we can view them on the right-hand side. So this is the whole point of why do you choose it the way that we're choosing it, so that actually the forms make sense and don't have poles. Right? On the initial, if you just work with the positive matrices, as soon as you have a minor of the matrix that becomes singular, then the form is not defined, so you can't make sense of it. So we're blowing up exactly what you need to blow up to capture the behavior of the forms. I mean, I'm raising it now. So and then the idea is to use exactly those forms which were useless earlier to get the relative forms. Yes, I remember earlier I made this long debate that beta 5, it's a funny form, but it does not give you a cohomology class in GL3. But it gives you a relative cohomology class in GL3. And so all the ones that have this extra one, the largest one that exists, that don't contribute here, they actually contribute on the other side, and those were the ones that pair. So the next step is, first of all, these beta forms extend smoothly. So this is the whole point of choosing the compactification correctly. They extend smoothly to this compactification. And then you have to ask, what does a form do on the boundary? How does a form restrict to the boundary? And there's a funny parallel in the story that somehow what happens on the boundary is somehow the same thing that happens on direct sums, on block diagonal sums. Because those forms only see the diagonal blocks when you're on the boundary. So there is a calculation that, so how do boundary strata even look like? So a single blow-up that goes into this construction can be parameterized as your matrix being ZA, ZB, ZB transpose C. And then the exceptional divisor would be Z equals 0. So you want to send Z to 0, so the matrix develops a kernel. So it's not positive definite anymore. And you're keeping track of how does it do that by keeping the leading order of this vanishing piece. And if you're there, then it turns out that the beta of such a form is beta k of A plus beta k of C plus vanishing contribution. First of all, it doesn't have a pole, so it extends to the boundary, so there's no pole when Z goes to 0. And as Z does go to 0, it has this decomposition. Just what I mentioned earlier happens for the block sum, because it turns out when you expand...
Can you say again what this x is?
So that's the parameter that I used as a coordinate on my
yes.
block.
And what is z?
Sorry, Z is the coordinate of the exceptional divisor on my block. So x is just the matrix, and this is just a choice of parameterizing matrix.
Is there a z in the fourth
Is it-
coordinate as well, or
Sorry.
like a c? Is there a z missing?
I mean, you could write x of Z if you want.
It's a
The
curve.
question is in the lower right corner. There's a C and there's no Z next to
I mean,
it.
you could, so this is, you could put arbitrary functions A, B, and C of Z here. Turns out for this limit, what matters is what happens to Z and the C in the limit. I mean, if you have higher orders of vanishing, you could, this is the blow up where just of this form. So you could put Z depends here, but then in here to leading order, you would only see C at Z equals 0. Okay, so this is a calculation. It's easy.
So this is some sort of, you've got C bars in there, right? Oh no.
No.
So it's some holomorphic arc or something, curve in the symmetric space. Z is a complex parameter.
Yeah, I mean, it's linear in a way. I don't know if you want to think of it as a curvy thing, but maybe with respect to the metric, it's curved. I don't know. Yeah, it's a curve that approaches the boundary.
So Z is a local coordinate for the exceptional divisor. That's what you're saying.
Yes. Okay. So you compute this, and now we're done. Because now what happens? Remember, we're looking at this one plays a special role, right? So the beta 4k plus 1 on the boundary of a 2k plus 1, shop B. Right, now this becomes, so there's lots of boundary strata that depend on what rational subvector space goes into the kernel or whatever. So there's lots of different strata, but they all look something like that. So if you go to any one of those, you know that this beta 4k plus 1 becomes beta 4k plus 1 of this one block plus beta 4k plus 1 of the other block. But we're talking about a block matrix, right? So this is 2k plus 1.
B or c?
Sorry? C. So if this is a 2k plus 1 matrix, then the block A or the block C have to be smaller than 2k plus 1. But one of the properties I showed you earlier is that this 4k plus 1, this is exactly the 2k plus 1 is the smallest matrix for which this form is not 0. So if you get any smaller matrix, it's 0. So this is 0. This is 0. So this one form that first switches on actually vanishes on the boundary. Therefore, it defines for you the relative cohomology class. And now, of course, you can wedge it with any of the other forms. It will still vanish on the boundary because one of the factors vanishes and the other ones are smooth. So what you conclude from this is something that now would actually fit next to this result. So what we've shown is that if you take the same forms,
Which G is in? Oh no, that's a 9.
sorry.
Yes, sorry.
I wish I could write some. So these are all the other forms. So I mean any polynomial and then also including this one. So together, these are all the invariant forms you can ever write down. I mean, either it includes this one or it doesn't, and these are the two possibilities. And all of those, we already said they map to 0 if you interpret them here. But what I now showed you is they map to compactly supported classes. Okay, now I have to write, of course, CK plus 1 over G, CK plus 1. So I've just shown you that they define elements in here. But now the claim is that they actually pair non-trivially, and therefore the fact that this is actually a map here shows that both of these maps are injective. So in a way, first of all, you just define elements, and then once you show that they pair, you get the injectivity of both of these. So just, well, I have to finish, right? So let me just say the last point of this argument. How many minutes?
One integral I have to compute, which is...
Wow, thank you. So the final remark is that the volume form on this quotient is proportional to the product. Yeah, so if you work it out, this has the right dimension. If you add up all these integers, it has exactly the dimension of the space. And this is the volume form. So if you integrate it, you get some positive number. It has been computed as a product of, no, sorry, yeah. It's a product of some zeta values, but for this, to realize that these forms actually pair up in this way. So now you're done, because if you take any monomial here, you take the monomial of all the other ones that you've missed, weighted with the extra one, and then this cup product that computes the pairing between homology compactly supported. So if you want to prove this, so if you go back to the fact to this beta 5 class in H5 of GL5, so how do we prove now that this is non-zero? Well, you know now that there's also a class called beta 9 in the compactly supported cohomology. There is a degree shift here because I replaced the space by this link, because I modeled out by these projective degrees of P5 mod GL5. And then these pair. So the Poincare duality says that the pairing of these two classes is given by integrating beta 5 wedge beta 9 over the entire space. Well, that's somehow, but it's not zero. Because that's the volume form. So I hope my goal was to show you the main idea. So the first idea was to use invariant forms on the space of matrices. Second idea was use Poincare duality to get the dual picture. The third idea was to replace the compactly supported thing by a relative form. So for that you needed a good compactification. So this is what went into this. And now all I want to say beyond that is just a remark that what happens when you go to the even rank case. So in this case, the quotient P2n mod GL2n is not orientable. So when you want to use Poincare duality, the Poincare duality is with the compactly supported cohomology with coefficients in the orientation bound. So if you want to represent this by forms, you need a form that when you now act with the group, it actually transforms the form not identically back to itself, but which multiplies it with the sign of the determinant. And there's the whole point of this paper. So what I've given you so far is actually just a review of previous work. What we do in our paper is we look at this Pfaffian form. So in the geometric analogy, when you think of Chern classes and so on, somehow you should think of these betas as kind of primitives of Chern classes, something like that. And then if you ask, in the even case, what's the Euler class? And that's what the Pfaffian is doing. So in the even case here, you can compute the Euler class from the Pfaffian of the curvature form and basis that is orthonormal with respect to the connection and so on and so forth. So what is a Pfaffian of a matrix? So if you have a 2n by 2n matrix, it's just this linear algebra, funny square root of a determinant, sum of permutations. Well, I should probably write the next one, otherwise you may guess something different. And now you know why it makes sense only for even. Or maybe I have to write the last one. So that's a Pfaffian, and what we put into this Pfaffian is the dx x inverse dx. Because you have to be a bit careful, right? You can't just take any algebra, commutative algebra, and throw in some matrices with weird form entries. Is it even well defined, right? So the good thing with this thing is dx, this is quadratic. This is a matrix whose entries are two forms. So those things commute. So this thing you can stick into any polynomial and it makes sense. So you take the Pfaffian of this. The Pfaffian has degree half the rank. So it's a degree n polynomial in the entries of this two-form matrix. So actually the whole thing has again degree 2n. So this is a 2n form. But if you just do it like this, you don't get a nicely behaved thing. What you have to do is you have to divide it by the square root of the determinant. Otherwise you don't get anything sensible. And if you do this, the thing is closed. And you can prove that it's invariant up to phi. So we call this phi. I really have to wrap up. So the key property is that that phi of g x g transpose is phi times the sign of the determinant. So that's exactly what you need. So that means if you use this phi, you can again define forms now with coefficients in this orientation bundle. And that's exactly taking on the dual side. So what happens there in the even case, when you hear 2n, you got to stop one earlier, and then you have to throw in this phi to n. And this is the volume form.
Minus 5.
E minus 3, thank you.
3, okay.
Modulo 4 plus 1, I wanted to go 1 before, so yes, and now if you use these forms, you get this corresponding result on the other side for the even ones. So those pair on the non-company support homology with the even ones. This explains a lot of the homology in the even case, and the thing that I really have no time to talk to, but I'm looking forward to learning much more about it this week. I think we're going to learn about it somewhat, I think. That there's a Hopf algebra structure on the direct sum of all of these cohomology groups. That means you can actually combine things in a different way using a new kind of product to cook up more forms. There's also an interpretation of that in terms of differential forms, but I really have no time to talk about this. And I didn't say anything about graphs, so ask me about graphs if you know about graphs.
What you said, so are there any more questions? Yes, Julia.
Can you compute the integral of any of these betas against graph classes to get like...
Against graph classes? Oh, that's what I spent a lot of time doing, yes. Yes. No, so indeed this is, I mean, our motivation was to do the graph complex, but of course you could also use graph classes to triangulate your space or whatever. So for every graph, you get a particular cycle, you get some subset of the space of matrices, and you can ask what are these integrals, do they mean something, I don't know. For graphs, we have a lot of technology to compute them, and quite a number of, well, a little hints. You can compute non-trivial examples, and we have used it to compute, to get cocycles for the graph complex. I don't know if that's the context you're interested in, but you do get interesting numbers. So actually it's quite interesting that, I mean, you may ask, okay, this is volume of the whole symmetric space, which is simple, it's a product of zeta values, okay. But now maybe you want to compute it by chopping it up into nice cones and then computing them individually. And what you do find is actually you get much more complicated periods, much more complicated integrals from these pieces than the whole thing. So in our paper, I put an example in the introduction of some graph of one of these examples. So it's beta 5, which 5, 6. So there's a graph with 12 edges and 6 loops. And it's a graph cocycle, and you compute this integral, and you get some polylogs at third roots of unity and second roots of unity and some stuff. But if you compute the cohomology class, it's actually associated to it. If you take a cycle, a lot of the mess cancels and it gets a bit simpler.
All right, let's thank Erik again.